Hello, welcome students. I welcome you all to the first lecture of Thermodynamics of Class 11 Physics brought to you by PhysicSpectra. Now, this is the first video of Thermodynamics and will be covering the whole chapter by some many other parts. So, let's get started. The topics that we are going to cover in today's lecture are this: intro, thermodynamic systems, thermodynamic variables, and thermal equilibrium leading to zeroth law of thermodynamics. So the first question that comes to the mind of students is, what is thermodynamics? Now you see, the name itself suggests that it is made up of two words, that is thermo and then dynamics. Now you all know that thermo means heat, just like you heard the term thermometer, which measures it. And dynamics means something related to motion, isn't it? Something related to motion. Now, when heat transfers from one body to another body, or you can say the temperature transfer from, the heat transfer from lower temperature to higher temperature, then all these studies that deals with heat, transfer of heat, conversion of work into heat or heat into work, all these things are studied in a parent chapter known as thermodynamics. Okay, now let us consider two systems. This system is system number 1 and this system is system number 2. Now the temperature of system number 1 is T1 and temperature of system number 2 is T2. Now if this T1 temperature is greater than T2, then we can say that heat will transfer from system 1 to system 2, because heat always gets transferred from higher temperature to lower temperature. This is the rule of nature. Just like potential energy, just like water, you can say, it always goes from higher to lower point, isn't it? Just like you studied in current electricity in class 10, that current always travels from higher potential to lower potential. Just like that, heat also travels from higher temperature to lower temperature. So what we had just said, that thermodynamics is the study of heat, temperature, and the conversion of work into heat, and vice versa. Okay, let's come into the thermodynamic systems. So in this chapter, we study three kinds of systems, like open system, closed system, and isolated system. Now let us study all these three systems one by one. Okay? Before that, you know one thing, that if we have any system, now this system has some particular temperature. We can set the temperature of the system, isn't it? It is in our hands. We can set the pressure of the system by vacuum tubes, anything. We can set its pressure. Now, we can also fix its volume, isn't it? We can take a large system or large container, you can say, or we can take a small container. Now, this we have called as system. But what happens outside to the system? Now see, all the universe, all the things that are outside to the system is called surrounding. Okay, now I am recording this lecture in my room. Now for me, if I consider my room to be my system, then all the natural environment outside my room or all the other things outside my room are the surroundings. So system and surroundings are two different spaces. System and surrounding together make the universe, together make the existence. Okay, so in this chapter we are considering three kinds of systems. The first one is the open system. So let us see one by one. Let's consider a system, but you see the upper layer of the system is open. Now let us take some water, let us take some liquid inside this system, or you can say a bucket we are taking. Now if we supply some heat to this system, and heat is denoted by Q. You can denote it by other name, but by convention we are just denoting it by Q. Now if you supply heat to this system, you will see that water vapors are emerging out of the system, isn't it? Let us take another color. Water vapors are emerging out of the system, and these water vapors are containing water molecules. These water molecules can be called as matter. We can call these water molecules as matter. Let us take another color. It is not, and there will be some transference of heat, isn't it? There will be some transference of heat from this system to the surrounding. Okay, so the system in which both matter and heat or energy, you can say, are transferred, are shared with the surrounding is called an open system. Clear? I think this is clear. Let us come to closed system. So in this case, you consider a system which is closed from all the sides. Okay, now just like the previous case, you consider some liquid, or you can also consider some gases inside this system. Now if you supply some heat to this system, then this system gets some internal energy. And you see one thing, there is no way that any matter that can escape from this system to the outside world, isn't it? There is no matter. The only thing that can escape from the system to the outside world is the energy, is the heat. Okay, is the heat. Now this is possible because we have taken a special kind of wall of the system. Okay, special kind of walls means the exact word for it would be diathermic wall. Yes, diathermic wall. Now diathermic wall means it just allows the heat, the energy to get transferred from inside the system to the surrounding. It does not allow transfer of any matter. Okay, so the system in which only energy is transferred, energy is shared with the surrounding but not matter, is called a closed system. I think it is clear. Now let us come to the most important system, that is called the isolated system. Now what is isolated system? Now just like closed system, we are considering a system closed from all the sides, but the only difference is that we are considering a special kind of wall. Now just like the previous case, we are taking some liquid, or you can also take some gases. We are supplying some heat to excite the molecules. Now this the surrounding, the walls that we have considered in this case is known as adiabatic walls. Remember the name, adiabatic walls. Now what does this wall do? It does not allow any matter or any heat to escape outside the system. That is, there is no exchange of heat or no exchange of matter outside the system. So you see, in an isolated system, it is completely isolated. There is no transfer of anything outside the surrounding. So I think it is clear to all of you. So let us come to the third topic of this chapter, that is intensive and extensive variables. Now what are intensive variables and what are extensive variables? Before that, we have to know what are variables. Now variables are something that can change. The value of something that can change. Just like in this chapter, we will be dealing with some special kind of variables, just like pressure. We are denoting pressure by P, that is temperature. Then S, that is specific heat capacity, volume, energy, that is internal energy. All these variables can be classified into two categories, broadly into two categories. That is intensive and extensive variables. Now what are intensive variables? First, let me classify all these things. out of these 5 variables that I have written in this slide, pressure and temperature and S, that is specific heat capacity, belongs to the intensive side, and on the other hand V and U, that is volume and the internal energy, belongs to the extensive side. Now what are intensive thermodynamic variables? The variables, that is P, T and S, which are independent of the size of the system, are called the intensive variables. Now what does it mean? It means that if we take a particular system and that system has some particular pressure, some particular temperature and some particular specific heat capacity. Now if we increase the size of the system or decrease the size of the system, for example, if we double the size of the system or if we halve the size of the system, then the pressure, temperature and specific heat capacity, etc., will remain same for the system. It is independent of the size of the system. But in case of extensive, we say that it is dependent on the size of the system. Okay. So, for example, we are taking the same system and we are increasing the size of the system. You will see that the volume of the system is also increased. If we halve the size of the system, the volume also gets halved. Just like this, the internal energy. Let's say some system has some gases, and all these gases have some internal energy in them. If we make a wall inside the system, then the internal energy of the two sides will also get halved or divided, isn't it? So let me just explain you in another slide. Let's say we have a container. Now in this container we are having some, or we can say system, in this system we are having some gaseous molecules. Now these gaseous molecules has some pressure, has some temperature, isn't it? Has some particular pressure and has some particular temperature. For example, let's say the temperature inside this system is 50 degrees centigrade. Now let us do one thing. We draw a wall just in the middle way. Now what will you expect? Will you expect that this chamber gets 25 degrees centigrade and this gets 25 degrees centigrade? Would you expect that? No, because you know that the temperature of this region 1 or region 2 will be exactly same and will be exactly equal to the original chamber. Because just by merely making half the full chamber does not make the two chambers of different temperatures, or it does not make them half. So this temperature is independent of the size of the system. The similar case is with the pressure. So this type of variables are called intensive variables. Clear? Now the other variables, just like the volume, just like the internal energy, which I have just explained to you, are extensive variables because these are dependent on the size of the system. Now let us come to the next topic, that is thermal equilibrium. So what do you mean by thermal equilibrium? For that, let us consider an example. Let us consider a chamber or a system in which there is a boundary, there is a dividing line made up of diathermic wall. Now you have already studied what does diathermic walls do. They just allow the transfer of heat and does not allow any transfer of matter. Okay. Now if we take some gaseous molecules or some liquid, anything you can say, and we just supply some heat in this first chamber. There are two chambers, one first and second. If you transfer some heat in this first chamber, this first chamber accepts the heat and it gets excited, it gets heated up, and simultaneously it tries to transfer some heat to the second chamber, isn't it? Because it is a diathermic wall. Now, as time progresses and as we stop this heat, we will see that a time comes when these two chambers will have the same amount of temperature, isn't it? And the transfer of heat will get stopped. Now, thermal equilibrium is achieved when this happens. Okay, so we can say that two bodies or two systems which are in contact are said to be in thermal equilibrium if both are at the same temperature. So if you say the temperature of this is T1 and temperature of this is T2, then at thermal equilibrium T2 equals to T1 or T1 equals to T2. There is no transfer of heat at all. Okay, I think it is clear, and based on this thermal equilibrium concept we get the 0th law of thermodynamics. So let's start our next topic. So let us come to the 0th law of thermodynamics. Now you see, this is named as 0th law. Why is it? You know, it is because of the first law is already discovered and after that the 0th law was discovered. Okay, so we have just named the first law as first law, so we can't change that name, no. So we have made the 0th law because it deals with the basics of temperature theory. It deals with the so in this law we will be using the concept of thermal equilibrium. So see, we are taking suppose a chamber and we are dividing the chamber like this. Let us take another color, in the chamber like this. This wall and this wall are of different types. So let us take a different color for it. Let us take blue color for it. These two walls are of different types. So what does these walls do? This red colored wall we are taking is adiabatic wall, and this blue colored wall we are taking is diathermic wall. And let us name the chambers as A, B and C. So in this whole chamber there are 3 chambers divided by some walls. So what happens is that this A and this C are in thermal equilibrium. Since we are considering diathermic wall between A and C, so heat will get transferred from A to C or vice versa, leading both of them to be in thermal equilibrium. So A and C will be in thermal equilibrium eventually. Again, B and C will also be in thermal equilibrium because B and C also share diathermic wall between them. So we can say B and C are also in thermal equilibrium. Now A and B can't be directly in thermal equilibrium, isn't it? They can't be directly in thermal equilibrium because we are considering adiabatic wall, and adiabatic wall does not allow any transfer of heat as well as matter. But since A and C are in thermal equilibrium, B and C are in thermal equilibrium, we can say that A and B are also in thermal equilibrium. We need not measure it, we will say it directly. But in real life it may not be necessary. If A is the friend of C and B is the friend of C, it is not necessary that A will be the friend of B, isn't it? But in case of heat, in case of thermodynamics, this happens because heat is a physical quantity, friendship is not. Okay. So this was all about our explanation about today's class.